we was not considering the effect of loss, but from today for a couple of weeks, I'm going to discuss the loss effect of transmission line. As the data rate is significantly increasing, the loss will become higher and higher, and it is becoming a big problem when we are designing the interconnection. So from today, I'm going to talk about loss effect. There are three kinds of loss in transmission line. First loss is coming from skin effect loss. You may remember that if we have transmission line, actually the current is conducted at the surface of transmission line, and that depth of current flow is called skin depth, delta. So even though you are using very thick copper lines to make the transmission line, actually the current is conducted at the surface. Because of that, we have surface resistance. And this skin depth actually decreases if you increase the frequencies. So if you want to have higher and higher data transmission through the interconnections, you're going to have higher and higher resistances. And it will create the attenuation of signal. So far in this class, we was not talking about the effect of signal attenuation. This attenuation will be represented by attenuation constant by skin effect loss, conductor loss. So if you are, even though you are sending certain frequency signals, as it propagates along the transmission line, it will suffer attenuations. And the attenuation is described by conductor attenuation constant multiplied by length of your transmission line. So if you have a longer interconnection, you're gonna have more attenuations. If your data rate is increasing, attenuation constant will increase, and because of that, you will have more attenuations. So even though at the transmitter side, you are sending 1 volt signal, at the receiver side, it could be less than 100 millivolt signal, and it could result in the voltage and timing reduction. And later, I'm going to show you that this skin effect loss effect will be proportional to square root of frequency. Second loss is coming from dielectric loss, and that will be represented by attenuation, dielectric attenuation constant. Oh, I'm sorry. I will say it is attenuation constant by dielectric loss. Later, I'm going to show you that this dielectric loss is proportional to frequencies. If this is the transmission line, we're going to have dielectric material, but it will have real term as well as imaginary term, and imaginary term will represent the loss, and it is coming from loss tangent. In the electromagnetic book, it is represented by loss tangent delta. So in the previous classes, we were assuming that this dielectric material is a perfect dielectric materials, but actually it has a loss. Especially the loss is proportional to frequencies. So if the frequency is becoming very higher and higher, your transmission line will have higher dielectric loss. Third loss is coming from radiation loss. This means that your transmission line is becoming an antenna, and your transmission line will generate electromagnetic field. This field will interfere with other sensitive circuits such as sensors or RF receiving front end. So especially this kind of loss will have big considerations when you are designing smartphones, because in the smartphone you have many wireless communication systems such as Wi-Fi, LTE, and Bluetooth. If some of these radiation frequencies are very close to those high frequency communication carrier frequencies, it will make more worse performance of your RF communication system. So this slide is a kind of summary of class today. So once again, I'd like to say that we have three important losses of actual transmission line, especially at very, very high frequencies. As I mentioned many times, high-speed interconnections such as for USB, next generation USB, PCI Express, and HDMI all goes beyond 10 gigabps, and some in the near future, the system will ask more than 100 gigabps. In those high data rate environment, we're gonna have very big considerations, and there are three important loss mechanisms. First one is skin effect loss, second one is dielectric loss, and third one is radiation loss. Today, I'm going to shortly discuss the physics associated with three losses. And also, in addition to that, I'm going to talk about the ISI, intersymbol interference, and that will be coming because of these three losses. And I'm going to talk about the I-diagram that has been affected by these three losses. As I mentioned before, this conductor, as I mentioned before, as this high frequency signal is traveling along the transmission line, it will suffer attenuations. This is attenuation constant. There are three different attenuation constant. Alpha C, that is coming from conductor loss, skin effect loss. Second loss is from dielectric loss, and third loss is radiation loss. If you have higher loss, you're gonna have more attenuation of signals. Also, you see that it is depending on the length of your interconnection. So if you make a shorter interconnections, you're gonna have less attenuations. That's why I'm keep telling you that in the future computer systems, it has to be three-dimensional to minimize the length of interconnection. Interesting thing is that this conductor loss, actually it is coming from skin effect loss, is proportional to square root of frequencies. I'm not going to spend too much time to derive equations to prove that skin effect loss attenuation constant is proportional to square root f, actually we can induce this relationship from transmission line theory or in microwave theory books. Probably I can send you some PDF files to show those derivations. But now I'm not going to do that, but I'm going to discuss more about the physical meaning of this attenuation constant. But meanwhile, as I mentioned in the previous explanations, I'm saying that conductor loss is proportional to square root of frequencies. Meanwhile, dielectric loss is proportional to frequencies. So because of that, there's some crossover frequencies near gigahertz frequencies. That means below gigahertz frequencies, skin effect loss is more dominant. However, above certain frequencies, the dielectric loss is dominant. As I mentioned previously, this dielectric loss will be represented by as loss tangent of your dielectric material, and this skin effect loss will be related to conductance of your copper and so on, and the dimensions of your transmission line. If your frequency is really becoming higher and higher over 10 gigahertz or 100 gigahertz, radiation loss will be dominant. And depending on your antenna structures, but I would say this radiation loss is typically proportional to square of the frequencies. So we have to fight against these three different losses. Typically, I would say from gigahertz to 100 gigahertz range, probably dielectric material is most dominant element. So if you want to have very clear eye diagram or clear data transmission, you have to choose your interconnection material who has very small loss tangent. But usually a material or structure who has very small loss tangent has usually very high price material, so it is very expensive. It's gonna be very expensive solution. Because of these three losses, conductor loss, dielectric loss, and radiation loss, we're gonna have some problems. Number one, which we will encounter, number one problem which we encounter when we are designing high-speed interconnection is signal attenuations. The amplitude of signal at the receiving side will be becoming smaller and smaller. Second problem related to this high loss is intersymbol interference. Later on, I will tell you that your voltage and timing at the receiver side will be very depending on the data pattern. Because of this high frequency loss, previous data bit pattern will affect current voltage and timing margin at the receiver side. So because of that, depending on your data pattern, you're gonna have different margin of voltage and timing. That is being called as intersymbol interference. So because of this signal attenuation and ISI, you're gonna have eye diagram distortion, and eye diagram distortion will give you smaller and smaller voltage and timing margin. Because of that, it is very difficult to design a receiver circuit and with minimal bit error rate. So because of this interconnection issues, ISI plus power and ground noise, it is very, very difficult to design the receiver circuit. So the receiver circuit is really, really becoming difficult. That's them now, they are asking, IO circuit designer are asking more better and better interconnection design in order to provide higher and more voltage and timing margin at the receiver side. Interconnection designer has to minimize these three different losses: conductor loss, dielectric loss, and radiation loss. Because of that, you have to understand the basic physics related to these three different losses. If you have this kind of I-diagram distortions, timing reference will be of some problem. So the digital waveform that is crossing at the center line will be different depending on the data because of ISI. So that is being called as jitter. And jitter is very big issues, and especially at higher data rate. And at the end of today's class, I'm going to talk about it more and more. So because of this jitter, we're gonna have smaller and smaller timing and voltage margin, and it will give us limit of data transmission rate and limit of computing performance, because now the computing performance is majorly limited by the data bandwidth between GPU and memory. And because of this timing and voltage margin reduction at a higher and higher, because if we have higher and higher data rate, we're going to have more high frequency losses, and we're going to have a smaller data rate, and we're going to have smaller computing performance. This is the overall picture of the class today. Junyoung, are you there? Can I speak to you? Could you summarize this page for me?
네, 트랜스미션 라인에는 이제 세 가지 로스 이펙트가 있는데, 첫 번째는 이제 컨덕터 로스에 해당하는 스킨 이펙트 로스랑, 이제 두 번째는 다이엘렉트릭 로스, 세 번째는 레디에이션 로스가 있습니다. 그중 이제 스킨 이펙트 로스는 프리퀀시에 이제 루트 스퀘어로 이제 비례하고, 다이엘렉트릭 로스는 이제 프리퀀시가 비례하고, 이제 레디에이션 로스는 프리퀀시 스퀘어로 이제 비례하기 때문에 저주파에서는 이제 컨덕터 로스를 이제 잘 설계해야 되고, 이제 1GHz에서 10GHz 사이의 영역에서는 다이엘렉트릭 로스를 잘 설계해야 되고, 이제 그 이상의 고주파에서 10GHz에서 100GHz 사이의 고주파에서는 레디에이션 로스가 이제 도미넌트하기 때문에 레디에이션 로스를 이제 잘 설계해야 되는데, 이런 로스 로스들로 인해서 시그널 어테뉴에이션, ISI, 아이다이 디스토션, 지터 등의 이제 악영향이 있기 때문에 잘 설계해야 된다고 이해했습니다.
그래서 이게 인터커넥션이 우리가 초반기 강의에서는 리플렉션, 임피던스 매칭, 크로스톡 그런 걸 위해서도 디퍼런셜 라인 쓰긴 하는데, 더 큰 문제, 데이터 레이트가 증가하면서 생기는 문제가 이 로스예요. 그래서 아마 couple of weeks 동안 이 로스 때문에 생기는 문제, 그래서 로스 때문에 ISI가 생기고, 그래서 볼티지 타이밍 마진이 줄어들어가는 이 문제가 모든 컴퓨팅 시스템, GPU, DRAM 사이에서도 지금 가장 인텔이든 삼성이든 머리 싸매는 문제죠. 근데 이걸 광으로 바꾼다고 하는 분들이 계신데, 그건 또 다른 어려운 점이 있고요. 그래서 그러면 결국 인터커넥션 숫자를 늘리는 수밖에 없는데, 그게 이제 코스트가 또 되고 그렇습니다. 그래서 이제 3차원으로 가야 된다는 말씀드리는데, 이게 2주간의 강의의 오버뷰가 되겠습니다. 계속 가보도록 하겠습니다. 이런 이론적인 거는 좀 지나도록 하겠습니다. Now, I'm not going to spend time to derive these equations. I'm saying that if you look into the transmission line theory book or microwave theory book, in some books, not all of the books, you can find some equations and you can see the derivation procedures of these equations. But this morning I was thinking about to spend some time to rigorously derive these equations, but it is a little bit too much. So I'm not going to do that today, and I'm going to talk just meaning of these equations more deeply. First term is conductor loss. As I discussed in the previous slide, it is coming from skin effect loss. At a high frequency, only in the transmission line, wave will propagate, and you remember that instantaneously there will be a current, opposite current at the top metal and bottom metal, and this current wave will propagate at the speed of light along the transmission line. And at the DC level, at the steady state, you see that it's gonna be a current into the end direction, and return current will come back to the ground. But at the high frequencies, instantaneous current will be induced at the top metal and bottom metal, and it appears only at the surface, very thin depth. Usually it is micrometers or less than micrometers. Even though you are using very thick metals, it doesn't help to reduce this conductor attenuation constant. Let's take a look at this equation, conductor attenuation constant. As I mentioned in the previous slide, it is proportional to the square root of frequencies. One interesting thing is that it has conductor of kappa. If you have metal who has small or higher conductivity, you're gonna have smaller attenuation constant. For example, let's assume you have a superconducting material who has infinite conductivity. You're gonna have zero attenuation constant. So that's why in the long future later, your whole computer system has to be put into the liquid nitrogen or liquid helium temperature. At some point, our whole computer system has to be put into the water system because we have to cool down the temperature because the CMOS transistor performance conductivity is increasing at a low temperature. And similarly, if we put our interconnection system at the superconductor, this conductivity is becoming infinite, then you're gonna have zero attenuation constant due to the skin effect loss. The first important observation here is the conductor loss is proportional to frequencies, square root of frequency. Second thing is this inversely proportional to conductivity of your materials. So kappa is probably silver is better than kappa, kappa is better than tungsten and other materials. So when you are designing certain interconnections using certain metals, you have to be carefully choose the conductivity of your metal. This tau is the wave impedance 377 ohm. That is the air property. So you are not gonna you are not be able. This is a constant, so you cannot control that. Here is D, thickness of your dielectric material in the transmission line. So it means that if you have higher D, thicker transmission line, you're gonna have smaller conductor loss. But unfortunately, in three-dimensional system, in this small computing system, D is becoming smaller and smaller. If you have a smaller D, electric field is becoming higher. That's why we are inducing more current at the surface. anyway, smaller d increase the conductor loss. So, and if you want to put your computer system into very low temperature to make a superconductor, it is very, very expensive. So what I'm saying is there's not much thing to do in this attenuation constant due to skin effect loss. As I mentioned that it is the attenuation is proportional to attenuation constant and G, length of your interconnection. So actually what I mean is that the only way we can achieve to lower down this attenuation constant is actually length of your interconnection. Length. Once again, repeatedly, I'm emphasizing that you have to make a very small semiconductor and small computer system. And that's how you can reduce the attenuation of your high-speed digital, especially if you want to achieve more than 20 gigabps or 100 gigabps. I'm assuming that in the near future, we will have pressure to achieve terabyte per second bandwidth, and it is becoming reality. There are two ways in this current period. One way to reduce this attenuation effect is the reduction of length. Second approach is equalizer. Third approach will be PAM4. These three subjects will be the main discussions of my class on Wednesday and next week. So equalizer is one way to overcome these high frequency losses, and PAM4 is another way to increase the data rate with this kind of limitations. But physically, number one approach is to reduce the length of interconnection. Second is increase the conductivity. And copper has certain conductivity. So if you want to really make a higher and higher conductivity using superconductors, you have to cool down your whole computing system nearly 0 degree Kelvin. Second, physics is related to dielectric attenuation constant. It is proportional to the frequencies, as I mentioned many times. And second important term is the loss tangent of your material. So some material may have loss tangent 0.01, but we have to choose 0.001 or 0.0001. So if there is some material scientist who is going to work on this kind of applications, we will ask them to find new PCB or new semiconductor who has very, very low loss tangent. But in case of silicon, you remember that silicon is semiconductors. That means depending on whether you choose semi-insulating substrate or P-type substrate or N-type substrate, the attenuation, there will be some hole or electrons. That means your dielectric materials may have certain conductivities. So you gotta, when you are designing interconnections as silicon wafers, you have to be very carefully design your interconnection. Otherwise, you're gonna suffer a very huge amount of loss tangent, and it will result in very high dielectric loss. So as I discussed in the previous slide, we have conductor loss term that is proportional to frequency, square root of frequency, and second term that is proportional to dielectric loss. So conductor attenuation constant is proportional to square root of frequencies, and dielectric loss is proportional to frequencies. So attenuation constant due to dielectric loss will increase linearly as a function of frequencies, but this conductor loss will saturate with the frequency, square root frequency, and there will be some crossover frequencies, F0. And how can I get this crossover frequency F0? We put alpha C is equal to alpha D. Then is a simple mathematics, and I was able to induce this equation. Crossover frequency. So below this crossover frequencies, conductor loss will be dominant, and above this frequency, dielectric loss will be dominant. In modern interconnection over 10 gigabps in these days, conductor loss, dielectric loss is becoming dominant. So, 현우, are you there?
네, 네, 교수님.
네, 여기까지 잠시 한번 설명해 보시겠습니까?
네, 일단 그 어테뉴에이트 컨스턴트 같은 경우는 총 두 가지 텀을 가지고 있는데 앞부분의 텀은 이제 컨덕터에 의한 로스 텀이고 두 번째는 이제 다이일렉트릭에 대한 로스 텀입니다. 그리고 컨덕터 로스 텀 같은 경우는 주파수의 루트배에 대해서 이제 비례하는 경향이 있고 또 수식을 보면 지금 컨덕터의 컨덕티비티를 기준해서 식이 서술되어 있는데 되게 컨덕티비티가 높은 물질을 사용하게 되면 로스를 확실히 줄일 수 있지만 요즘 많이 사용하고 있는 스몰 사이즈 시스템 같은 경우는 다이일렉트릭의 티크니스가 매우 작기 때문에 그 로스 텀이 무조건적으로 나올 수밖에 없는 상황이고 이제 다이일렉트릭 텀 같은 경우는 주파수에 비례하는 경향을 보이고 있고 이것도 마찬가지로 로스 탄젠트라는 텀이 있어서 저희 이 두 가지 로스를 전부 고려한 그 디자인이 잘 이루어져야 한다고 이해했습니다.
결국 이게 자연적으로 존재할 수밖에 없기 때문에 여기에 곱하기가 되는 게 길이니까 주파수가 올라가면 길이를 짧게 해야 된다. 뭐 이렇게밖에 말씀을 드릴 수 없고 자연 현상의 이 어테뉴에이션 컨스탄트를 줄일 수 있는 방법은 온도를 줄이는 것밖에 없다. 그런데 요즘 GPU나 뭐 다 또 뜨거워지거든요. 파워 소모가. 그런 점들이 이제 충돌 요소인데 살짝 미리 얘기하면 이런 아까 조금 전에 말한 것처럼 이 길이를 극복하기 위해 줄이는 게 하나가 있고 그 다음에 이제 이퀄라이저와 팜4라는 게 이제 새롭게 등장을 합니다. 먼 미래에는 광인터 커넥션으로 갈 수도 있지만 광인터 커넥션은 전기를 광으로 바꾸는 과정에서 로스가 또 커요. 이러지도 저러지도 못해서 결국 제가 3차원적으로 쌓고 구멍을 뚫자 이런 제 생각을 이제부터 갖게 됐습니다. Thank you. So this is another summary of a previous slide. So if we increase the conductivity of your metal, conductor loss will decrease from higher value to smaller value. Also, if you increase the distance between the two metals, that is not actual, that is not feasible in these days anymore. But anyway, if you increase the thickness of your dielectric material, conductor attenuation constant will be decreasing. Also, another important observation is that if we reduce the attenuation, loss tangent, dielectric attenuation constant will decrease. Now, this is very important part of the class today. Please pay attention to that. 여러분들 다 이제 여기서부터 또 집중해 주길 원해요. 제 강의 스타일이 큰 스케일로 가서 점점 깊이 가는데 이 부분이 제일 중요합니다. Now let's talk about the eye diagram. In this case, we have some losses, higher losses. Please pay attention to that. I'm going to draw the voltage waveform at the receiver side with the different data patterns. First, let's assume that we have higher logic level at the receiver side, then it's going to be near 1. And let's again, at the second bit, we have high voltage level, DC level 1. I'm assuming that from infinitely long, we have higher voltage level, 1, 1, 1, 1, 1, 1, 1, 1. So now I'm trying to discuss two effects, data dependent effect and high frequency loss effect. If they are coupled together, it will reduce the voltage and timing margin. That's what I'm going to discuss right now. Let's assume from long time ago, I assume that the data pattern was 1, 1, 1, 1, 1, 1, 1, 1. If you are sending image, digital image, let's assume your TV screen is all black, all white, then probably data pattern could be 1, 1, or 1. Now at third bit, I'm assuming that it is becoming 0. It has to come down. But because of loss, the voltage at this transition cannot suddenly change to 0. Ideally, it has to go back to 0. But because of attenuation nature, it cannot reach a full 0 voltage level. It has to come back to certain level. It will be proportional to attenuation constant and length L. Ideally, at the voltage level at the receiver is being assumed to go to the 0 level if attenuation constant is becoming 0. It is ideal, that is the case of ideal transmission line, but because of attenuation constant, it will suffer certain RC type of exponential decay type of decay, and it will reach to 0 point. Let's assume that it is going, but data pattern is 0, 1, 1, 0. Suddenly it is changing back to 1. Then this voltage waveform has to go back to 1 again. And then I'm assuming that it will infinitely, it is becoming 1, 1, 1, 1, 1, 1. So what I'm saying is that ideally, at the receiver, it has to have this kind of waveform 1, 1, 1, 1, 1, 0, 1, 1, 1, 1. But actual waveform at the receiver side will have this kind of a smooth curve, and this lower level at the receiver voltage level at the receiver side is gonna be higher than ideal 0 level. And this kind of effect, the voltage level at this point is affected by the previous data pattern that is being called as intersymbol interference. I would say that is gonna be the worst case data pattern. There might be many different definition of worst case data pattern, but in this examples and discussions, I would say this is gonna be a worst case data pattern. Now, I'm talking about another case where infinitely long we have 0, 0, 0, 0 data pattern, and suddenly in section C we have bit 1, then we're gonna have smoothly increasing, but not infinitely fast, but smooth the voltage waveform, and we are assuming the data pattern is coming back to 0, 0, 0, 0, 0, then it has to come back. So what I'm saying is that ideally, digital data waveform has to be like that at the receiver side, and digital waveform has to be this waveform, in this case of data pattern 0, 1, 0. So we're gonna have full square voltage and timing margin to secure setup and hold time at the receiver side. If you have clear opening, we have more timing and voltage margin for setup and holding time, and we may have very clear voltage to determine whether it is logically high or low. At the receiver, you may have AD converters or what kind of amplifying circuits, and they may have less problem to determine whether it is logically higher or zero. But actually, what is happening is here we have only very, very small window to reduce the power consumption for this high-speed interconnection. Usually, let's assume this is 1 volt level. Now, this is becoming 100 millivolt level to reduce the power consumption. And so this is becoming less than 10 millivolts. And this timing margin is usually in this stage, probably 100 picosecond is extremely small. So here, voltage timing margin could be less than 10 picosecond. So you have to design your receiver circuit to determine very clearly logic high or low with this very small voltage margin and timing margin. Why this is happening? Because what I'm saying is that this is coming from the loss of this transmission line, and this loss has 3 terms: conductor loss and dielectric loss and radiation loss. If we have these losses, we cannot have infinite fast transition to make the maximum eye opening, but actually we're gonna suffer very small voltage and timing margin at the receiver side. This is a really, really big issues to achieve very. Let's assume you have TV and you have set-top box. You have to send data using HDMI. And between computer and CPU and GPU, you have to use the PCI Express. Probably if DRAM and GPU, you may have many different interconnection types, but all these cases, we want to increase the data bandwidth to maximize the AI performance or metaverse calculations. But because of this high frequency loss, we're gonna have very small voltage and timing margin. 정현, 종현,
교수님,
네, 간단히 설명해 주시겠습니까? 예.
우선 인터커넥션에 이제 로스가 존재하는데 그 어테뉴에이션 컨스턴트를 구해보면 리시버 단에서 데이터가 변화할 때 그 디케이가 존재하게 되고 결국 그 아이디어란 0이나 1의 레벨에 도달하지 못하게 되고, 그래서 그 로직이 하이인지 로우인지 분간하기 어려운 상황이 발생한다고 이해했습니다. 또 아이다이어그램 관점에서 분석을 해보면 이 ISI 때문에 이제 볼테지랑 타임 마진이 줄면서 이 I가 작아지게 된다고 이해했습니다.
그렇습니다. 컴퓨팅 그 퍼포먼스 그게 AI 컴퓨터든 서버든 요즘은 이게 폰 노이만 구조라서 한 군데 다 할 수가 없어요. 데이터 생산하는 데와 저장하는 데 디스플레이가 다 분리되어 있어서 또 클라우드 컴퓨팅에서는 또 데이터 센터에서 계산을 하고 빨리빨리 데이터를 주고 받아야 되는데 거리가 떨어져 있다 보면 로스가 생기고 고주파에서 결국 여기서 보는 것처럼 우리 아이디어란 디지털은 1에서 0으로 탁탁 깨끗하게 떨어져야 되는데 이렇게 스무스하게 떨어지면서 리시버 회로에서 이거를 1이냐 0이냐를 판독할 때 굉장히 마진이 줄어들었다. 네, 그래서 여기서가 몇 가지 메시지가 있는데 로스가 굉장히 문제더라. 로스 때문에 ISI가 생기더라. ISI 때문에 이 데이터 디펜던트 하다는 거예요. ISI라는 거는 데이터 디펜던트 하면서 근데 우리가 이제 디지털이라는 거는 데이터가 올 화이트일 수도 있고 올 블랙일 수도 있고 원 비트만 1이나 0이나 되는 다양한 데이터 패턴 속에서도 셋업 홀드 타임을 유지해주고 볼테이지 마진을 확보해줘야 리시버 서킷에서 동작을 하게 되는데 그게 굉장히 어려워졌다. 그 중에 하나가 바로 로스 때문이다. 물론 여기에 그리지는 않았지만 크로스톡도 이런 문제를 만들고 파워 서플라이 노이즈도 이런 게 지금 여기에 여러 가지가 지금 우리가 지금 이렇게 생기는 거에 ISI만 지금 얘기하고 있잖아요. 두 번째가 이제 크로스톡이 생기고 세 번째가 리플렉션이 생기고 네 번째가 파워 그라운드 노이즈가 이런 것들이 다 중첩되면서 더 많은 스위칭이 일어나고 더 빨리 하면서 동시에 이 타이밍 볼테이지 마진을 확보하기가 굉장히 어려워졌다. 그래서 1, 2, 3, 4가 되게 중요한 요즘 그 반도체 설계 주제고요. 이걸 극복하기 위한 이제 꼼수 방법이 이퀄라이저가 있고 팜4가 있고 그렇습니다. 이런 것들이 또 중요한 회로들이 되고 또 새로운 방법이 되겠습니다. 그래서 지금 이제 뭐 이렇게 슬라이드 몇 장으로 이렇게 설명하지만 인텔이든 삼성이든 엔비디아든 기술적으로 여기에 꽉 막혀 있는 측면이 제 생각에 한 30-40% 앞으로 어떻게 반도체나 컴퓨터 구조가 바뀌어야 될지 I/O 스펙이 바뀔지 DDR이든 GDDR이든 HBM이든 다 그리고 HDMI, PCI Express 전부 다 그런 궤적을 갈 것 같습니다. 그래서 여러분들이 그거를 이해하도록 지금 강의를 하고 있는 거고요. 가끔 말씀드리지만 우리 강의가 봄부터 시작해서 트랜스미션 라인이 있어야 되고 임피던스와 전파 속도가 주파수에 상관없어야 된다고 그랬는데 그리고 임피던스 그러니까 반사가 없게 임피던스를 맞춰야 되고 크로스톡을 없애야 돼. 그래서 디퍼런셜 시그널을 쓴다고 했는데 알고 보니까 그 다 해결해도 더 큰 문제. 이건 자연의 현상이기 때문에 우리가 어쩔 수 없는 이런 문제가 등장하고 있습니다. This is for the case of heavily lossy line. But let's assume that we have small loss line, then ideally this line has to have a fast transitions, instantaneous transition case. Also, we can have instantaneous transition case. This is textbook style I-diagram, but in actual case, in the worst case, we're gonna have very small eye opening. If we have moderate loss interconnection, we're gonna have certain eye openings. So depending on your interconnection design, you can have very small eye opening, ideal opening, or moderate opening. So we're gonna have many different cases. So sometimes when you wanna quantify your quality of interconnection, you have to obtain the I-diagram. So one way to obtain the I-diagram is measurement. But if your interconnection is inside the chip or inside your computer, it is very difficult to measure the I-diagram. If you want to measure I-diagram, you have touched the transmission line using the oscilloscope probes. But the oscilloscope probe itself has capacitive load, and the oscilloscope probe itself has data bandwidth limit. Your oscilloscope and your probe is not a perfect measurement tool. It has certain limitations because of the capacitive load and transmission line impedance. And also you have to use probe structures and cables. And then you're gonna also have high frequency loss as well. So measurement has very, very limited. Sometimes in our laboratory, our students are working with some semiconductor companies in Korea. We have big contribution to them recently because we help them to design new structures to be able to measure this bandwidth. Without measurement, we don't know what is the problem. Sometimes it is coming from crosstalk or ISI or power supply noise. Sometimes you want to verify using the measurement. So measurement is really important, but it has certain limit. Second is the simulation. In order to simulate I-diagram pretty well, you have to have very clear and high frequency models of your interconnection, as well as your I/O circuits. Sometimes your interconnection starts from your chip, package, PCB, socket, daughter board, and motherboard, and there are many interconnection levels between transmitter and receiver. So, but sometimes the IC vendors does not want to release their I/O circuit model. Sometimes they are supplying the model using IBIS. But in these days, some companies, big nationally, globally big companies, they don't want to release even their IBIS model. So simulation is really, really difficult. If you are you want to be a good interconnection designer or I/O circuit designers, you have to raise your capability of modeling and simulations of interconnection. But another problem of this simulation is that you have to do the three-dimensional simulation because it is three-dimensional structures. So it is simulation time is really, really high. In order to have full I-diagram simulations, you have to simulate many, many different types of data patterns. The data pattern combination could be 10 to 12 or 10 to 15. If it takes 1 second to obtain one I-diagram of data patterns, if you multiply that to 10 to 15, it's gonna be 100 years. So it is another very difficult job to obtain this I-diagram. So in our laboratory, we are trying to use the AI machines, artificial intelligence, to obtain this I-diagram. 혹시 지훈이나 준상이 있어요? They may not be here today because who is there? 준상이 목소리가 잘 안 들려요.
네. 잠시만요.
어제 밤샜나요? 텀 프로젝트에 한번 여기에서 있는 얘기 한번 제가 막 떠들었던 얘기 한번 해볼래요?
아까 하이로스 라인에서
약간 더 크게.
하이로스 라인에서는 애니메이션에 의해서 이제 아이가 작게 보였기 때문에 롤로스 라인에서는 이제 어테뉴에이션이 작게 돼서 아예 그림이 커지게 되고 그래서 그리고 이 측정을 함에 있어서 이 측정하고 시뮬레이션을 함에 있어서 굉장히 민감하기 때문에 프로브 팁이 프로브 팁이 필요하고 또 시뮬레이션을 할때 시뮬레이션과 함께 보면은 이제 타임 도메인에서의 결과 같은데 충분한 양의 시뮬레이션을 통해서 이제 BR을 고려해서 아이를 만들어내야지 정확한 아이를 쓸 수가 있다. 이렇게 말씀 주셨습니다.
고맙습니다. 조금 전에 오른쪽 measurement, simulation, AI 이런 쪽은 아주 중요한 우리 엔지니어로서 중요한 물론 물리적인 개념도 알아야 되지만 이게 아트 레벨에 가깝다. 그래서 여러분들 전공하기에 딱 좋은 것 같습니다. 측정도 어렵고 시뮬레이션 시간이 너무 많이 걸리고 모델을 잘해. 측정은 그 자체가 이미 그 시스템 자체를 퍼터베이션 하는 거기 때문에 자기가 측정하는 게 리얼 값이 아니라는 얘기고 우리 연구실에서는 한번 AI를 믿어볼까 이런 겁니다. 또 하나 미닝은 인터커넥션을 퀄리티를 이렇게 보기 위해서 누적돼서 이렇게 다양한 데이터 패턴을 누적해서 그려서 얼마나 볼테이지와 타이밍 마진이 확보되는가 이거를 아이 다이어그램이라고 합니다. 자, 오늘은 여러분들 중간고사 준비도 해야 되고 그래서 여기까지 하도록 하겠습니다. 다음 시간에 아이 다이어그램만 가지고 또 계속 얘기해 보겠습니다. 아이 다이어그램 중에서 이 시간축의 그 마진을 결정하는 지터라는 텀이 있어요. 이거를 또 한번 집중적으로 얘기해 보겠습니다. 오늘 여기까지 마치고요. 오늘 오후에 또 뵙겠습니다. 여러분 집중해 주셔서 감사합니다.